This content is AI generated for informational purposes only and should not be directly used for clinical decision-making.
Hello and welcome back to the Neurosurgery Hub Podcast. I'm Dr. Aris, a senior attending in neurosurgery.
And I'm Dr. Elara, a research fellow. Today we're looking at a fascinating new study from the Journal of Applied Clinical Medical Physics, published in 2026. The paper is titled Method for Simultaneous Selection of Treatment Isocenters and Margins for Polymetastatic Extracranial Stereotactic Ablative Radiotherapy by Slagowski and colleagues from the University of Wisconsin-Madison.
Now, for our neurosurgical audience, this might initially sound like it's purely in the realm of radiation oncology or medical physics, but the concepts are deeply rooted in what we do every day with stereotactic radiosurgery, or SRS for brain metastases. We've seen a massive shift in the last few years toward treating polymetastatic disease. We used to stop at 3 or 4 lesions, but trials like SaberComet and SaberComet-10 have pushed those boundaries to 5, 10, and even more lesions.
Exactly. And while the paper focuses on extracranial sites, specifically lung cases, the technical challenge is one we face in the cranium. How do we treat multiple targets efficiently without sacrificing accuracy? Historically, we've used an individual isocenter for each target to minimize setup uncertainty. But if you have 10 lesions, 10 isocenters make for a very long day for the patient and the clinical team.
Right. It's the single isocenter multi-target, or SIMT approach. It's efficient, but it introduces a specific problem, rotational error. When a lesion is far away from the isocenter, even a tiny 1-degree rotation of the patient results in a significant translational miss at the target site. This study addresses that head-on. Elara, walk us through the core objective of the researchers.
The team wanted to develop an end-to-end method to simultaneously cluster tumor targets and optimize both the number and the position of isocenters. The goal is to minimize the additional margins required to maintain target coverage as that tumor-to-isocenter distance increases. They used a k-means clustering algorithm to do this.
K-means is a classic unsupervised learning algorithm, but using it here to balance treatment efficiency against normal tissue sparing is clever. For the residents listening, remember that the planning target volume, or PTV, is an expansion of the clinical target volume, or CTV, to account for uncertainties. If you use one isocenter for 2 distant lung nodules, your margins have to grow to ensure you still hit the targets despite rotations.
And that's where the math gets intense. The researchers used a statistical formalism, specifically the Chang model, to determine the margin required for a 95% coverage probability. They modeled translational uncertainties at 5 millimeters and then looked at rotational uncertainties at 1, 2, and 3 degrees.
Let's dive into the methodology. They evaluated this on 20 clinical lung cases. These weren't simple cases. They had between 2 and 21 targets per patient. The distances between targets ranged from about 4 centimeters to over 32 centimeters.
That's a huge range. They compared their k-means approach against 2 things. First, a hybrid optimization method, which is much more computationally heavy. And second, the standard clinical practice of using fixed 5 millimeter or 10 millimeter isotropic margins.
And what did they find regarding the k-means performance?
It was incredibly efficient. The median runtime for the k-means algorithm was only 0.19 seconds. Compare that to the reference hybrid optimization method, which took over 300 seconds, nearly 5 minutes.
In a busy clinic, that speed matters. But did they sacrifice accuracy for speed?
Surprisingly, no. The total margin volume determined by k-means showed no significant difference. The p-value is 0.94, compared to the more complex hybrid optimization. We're talking median differences of less than 0.2% in margin volume, even at 3 degrees of rotational uncertainty.
That's a crucial point for our residents. If a simplified algorithm like k-means can give you the same clinical result as a complex derivative-free optimization, it's a win for the workflow. But the real meat of the paper is about the relationship between the number of isocenters and the total margin volume. This is the sweet spot we're always looking for.
Right. They found that increasing the number of isocenters, let's call that n, for a given patient significantly reduced the total margin volume, up to a point. For example, moving from 1 isocenter, n equals 1, to 2 isocenters, n equals 2, reduced the median total margin volume by 31%.
31% is massive when you're trying to spare lung tissue, or in our case, healthy brain parenchyma.
It is. And then moving from 2 isocenters to 3 gave another 15.7% reduction. But after that, they saw diminishing returns. When they went from n equals 4 to n equals 6, the reductions were much smaller, only about 6%, 5%, and 3% respectively.
This is a key takeaway for practicing neurosurgeons and radiation oncologists. There's a rule of diminishing returns here. You get the most bang for your buck by splitting your targets into 2 or 3 clusters. Adding a 4th or 5th isocenter adds a lot of treatment time and complexity, but doesn't significantly reduce the volume of healthy tissue you're hitting.
Exactly. And the paper notes that if you use fixed margins, like a standard 5mm or 10mm margin, you are often either undercovering the target at large distances or over-irradiating normal tissue for targets close to the isocenter. The K-means method allows for a simultaneous selection, where the margin is tailored to the distance.
Let's talk about the rotational uncertainty. They modeled 1, 2, and 3 degrees. In neurosurgery, with a head frame or high-end mask-based systems, we like to think our rotations are sub-degree. But in the extracranial world, the thorax or abdomen, 3 degrees of rotation is a very real possibility.
Definitely. And as that rotational uncertainty increases, the benefit of the K-means clustering becomes even more apparent. If you're at 3 degrees of uncertainty and you're using a single isocenter for a target 20 centimeters away, your required margin becomes massive to maintain that 95% coverage probability.
I think it's important to highlight the target to isocenter distance mentioned in the paper. They emphasize that translational errors, like setup, are constant, but the rotational component of the error is a function of the distance d. The formula they used accounts for both. As d increases, the rotational error dominates the margin requirement.
Which is why the clustering is so effective. By picking an isocenter that is centrally located within a cluster of tumors, you minimize the maximum D for any single tumor in that cluster.
Now, for our medical students, why does this matter for the patient? It's about the integral dose. If we use a 10mm margin when we only needed 6mm because we positioned our isocenter better, we are sparing a significant volume of normal tissue. In the lung, that means less radiation pneumonitis. In the brain, that means less risk of radionecrosis and cognitive decline.
And the study also touches on treatment efficiency. If we have 21 targets, as one of their cases did, and we can group them into 3 or 4 isocenters using this algorithm, we've made a treatment that would have been impossible or incredibly exhausting into something manageable in a standard time slot.
Was there anything in the results about the target volumes themselves?
Yes, the targets were quite varied, from very small lesions of 0.07 cubic centimeters up to 41 cubic centimeters. The target-to-target distances were also widely distributed, up to 32.4 centimeters. The K-means method held up across this whole spectrum of complexity.
It's a robust study. It validates that we don't need to overcomplicate the math to get a significant clinical benefit. A simple clustering algorithm can optimize our isocenters and, more importantly, tell us exactly what margin we need for each specific target based on its distance from that isocenter.
One thing I found interesting was the benchmark against a derivative-free hybrid optimization. The fact that the K-means total margin volume had a median difference of only 0.03% for 1-degree rotations really shows how well-suited K-means is for this geometric problem.
It really highlights that in medical physics, sometimes the good enough is actually nearly perfect when you factor in clinical speed. Elara, if you were summarizing the clinical take-home for a neurosurgeon resident, what would you say?
I'd say, first, don't settle for isotropic fixed margins when treating multiple distant targets. Your margin should be a function of the distance from the isocenter. Second, if you have more than 3 or 4 targets, consider using the K-means approach to find 2 or 3 isocenter locations. It's the most efficient way to drastically reduce your total margin volume without making the treatment plan overly complex.
And I would add, remember that the goal is always the balance between ablative tumor doses and normal tissue sparing. This paper gives us a mathematical roadmap to achieve that balance in the new era of polymetastatic disease. It's no longer about whether we can treat 10 lesions, but how we can do it with the highest precision and the lowest toxicity.
Well said. It's an exciting time for the field, especially as these extracranial techniques start to inform our intracranial workflows and vice versa.
Absolutely. Well, that's all the time we have for today's deep dive. Thank you, Dr. Elara, for breaking down the technical bits for us.
My pleasure.
And thank you to our listeners. You can find the full paper, Method for Simultaneous Selection of Treatment Isocenters and Margins, in the Journal of Applied Clinical Medical Physics. We'll see you next time on the Neurosurgery Hub podcast.
Goodbye, everyone.